Hello and welcome Nord Anglia to today's MIT Abstract on Mathematics with MIT graduate student John Urschel. I'm your host, Fatima Husain, and I'm a graduate student at MIT studying ancient Earth. Before we begin, I'd like to cue our listeners into what an abstract actually is. An abstract is just a snapshot or a summary of a greater work of research or writing. And with this series, MIT Abstracts, we're bringing abstracts of inspiring MIT experts straight to you and your screens all around the world. Now, I am super duper excited to introduce you to our expert today, John Urschel, who is a PhD candidate in the MIT Department of Mathematics. Hey, John, how are you?
Hey, I'm doing well. How are you doing this morning?
I'm doing great. I have the Alchemist behind me at MIT, and I'm wearing my MIT, math t-shirt for you. So I am so pumped for this.
Good. Well, we had better get started. So
Fantastic.
The way this is going to go is I'd like to talk for maybe 10, 15 minutes about not just math or my area of math, but how I got into math, what I think is cool about math, and then focus somewhat on my research in math, which is very much focused on an area called linear algebra. And in fact, using tools and ideas in linear algebra to solve real world problems. But first, let me share my screen. I made a little slideshow for you all. So that right there is a picture of me at MIT at my chalkboard pre-pandemic. I had much less hair. This year has not been kind to me. Okay, so I want to start by talking about my experiences with math as a child. So this is me as a kid with my mom and my grandma. My mom always loved math when she was a kid and growing up, but she actually ended up not going into a career in STEM because she was a little sort of self-conscious about her math ability and her ability in science. And so she ended up not taking the math route and she ended up regretting it. And so when I was growing up as a kid, I always liked shapes, I always liked puzzles, and my mom saw that and she just jumped on it. And so my mom was my sort of biggest motivator. And as a kid, she would buy me like tons of little puzzle books. Like I would solve all these different like little puzzles at home. Like I would always solve these like zebra type puzzles where, they give you all these different facts and they tell you this person lives in this house, this person owns this car, and you would have to like deduce who lives where. I would do like little magic sums and magic products. And this is really, in my opinion, how I first got into math. Because all these things sound like games. He sounds like fun little things you might just do in the morning or do at night. But these are actual sort of exercises that help train you to think mathematically, to help you take in information, think about how you can use them, and use that information to come to a conclusion. One thing you should know that is slightly off topic, but I feel obligated to mention, is that although I am a mathematician, I also was a professional football player. And so while studying math and while being very interested in math, I also enjoyed doing other things like sports. I played football in high school, I played football in college. But in college, when I started taking math classes, I wasn't even a math major. I was majoring in aerospace engineering, actually, because my mother told me I was going to be an aerospace engineer. And I said, okay, Mom. But I ended up taking math classes in college, and they ended up being my favorite classes. And the reason why my math classes were my favorite is I found often my engineering classes, although very good classes, were very concerned with how. We know we have some tools, we know we have some formulas, we know certain things. How do we use them to build a bridge? How do we use them to mine oil or whatever it may be? And I found that in my math classes, I was really interested and they really focused on the question of why. Why is a formula true? Why can we do this? Why do we know this or why do we know that? And so I actually took a math class, and the way I got into sort of like math research and being a mathematician is I had a professor and he thought I was good at math and he took an interest in me The class, it was a calculus class. So it was a class where we more or less prove some of the results of calculus. And he asked me if I was interested in doing math research. He gave me this book, Chaos: An Introduction to Dynamical Systems. He told me to read the first chapter, and he said, at the end of the first chapter, there's this exercise, period 3 implies chaos. And he's told me to go home and try to solve it and bring back the solution to him. And this had nothing to do with our class. And so I spent a week just reading through this book and trying all these different ideas and trying to prove this thing. And when I finally proved it at the end of the week, this like amazing feeling of accomplishment just washed over me. And I brought the solution to him, and he was quite pleased with me. And he asked me if I'd like to do a research project with him. And first of all, if you haven't heard of this idea of period 3 implies chaos, what it means is, suppose you have a dynamical system, which is something which changes states over time. And suppose you know that there's some initial state where something happens, maybe a day goes by, it goes to another state, another day goes by, it goes to another state, but on the third day, it comes back to the original state. That actually implies that it has periods of pretty much all orders. It implies that your system is actually chaotic. And so this was the exercise he gave me. And after that, I worked on a research project with him for the better part of a year, and it eventually became a publishable work. And it was a work in celestial mechanics involving a 3-body problem. And once I got the opportunity to do math research, I have to say I was hooked. There's just something amazing about seeing these like interesting unsolved problems and being able to solve something that no one else has ever solved before. And there's something really just really sort of exhilarating about that. Even more exhilarating than American football, even better. So I got my undergrad degree at Penn State. I played professional football for a little while, but the part that I want to focus on is this is MIT Abstracts. I started my PhD at MIT. So this was the initial picture. And while at MIT, I have to say, I've just been floored by all the amazing and brilliant mathematicians here. All of them so passionate about whatever area of math they're working on, making these amazing contributions. It's just such a great sort of exhilarating math environment. And while at MIT, I've been working on research in something called linear algebra. So what's linear algebra? Imagine some of you, maybe you haven't quite gotten there yet, but at some point, when you need to solve an equation, maybe you need to solve an equation like x plus 3 equals 5. And what you might do is you might subtract 3 from both sides, and then you get x equals 2. X plus 3 equals 5 is an example of a linear equation. But sometimes things get even more complicated, and you might have linear equations with more than one variable. Maybe there's an x and there's a y. And you have 2 equations that you need to solve for some reason. Maybe the reason is, let's say you have, I'm going to make up a completely random example. Suppose you have, suppose you need to grab 7 boxes, and boxes of one type only fit 2 books in them, and boxes of the other type fit 3 books in them, and you have 16 books, and you want to have exactly 7 boxes. How many of each box type should you get? Well, X and Y tell you that. And one way you could try to solve this system of equations is you could maybe solve for X in the bottom equation, maybe X equals 7 minus Y, and plug in 7 minus Y for X in the top equation, and then solve for Y. You can do this when you have 2 equations, but sometimes in practice, you have a lot more equations. And so it's important to think about techniques to solve these type of problems that are robust to maybe many equations in many variables. And so here you can write this 2x2 linear system as something that we'll call a matrix times something called a vector equals a vector, which is just a way to encode this linear equation that we started with. And then you can do some sort of operation on this matrix and this vector to try to come up with the solution. And so what I did here is something called Gaussian elimination, which allowed me to convert this linear system into some matrix, allowed me to subtract some fraction of the first equation from the second, solve for y, and then solve for x. And now I'm showing this to you for a 2x2 example, but really what you should think about is solving this where maybe the number of equations is maybe 1,000,000 or 1,000,000,000, or maybe we're not trying to solve linear systems, which we often write as ax equals b, but maybe we're trying to solve an eigenvalue problem, something called ax equals lambda x, where you can imagine what we're doing is we're trying to find directions in which this matrix is invariant in some sense. We imagine we have some direction, we apply our matrix to it, and it maybe just stretches it or it shrinks it, but it doesn't really move it off its line. And this is really important because it helps us figure out directions which are really important, that are really important to our matrix. And I'll talk about that a little bit more. Linear algebra can be used to solve a wide range of problems. For instance, if you're an engineer or a physicist or a chemist, oftentimes a lot of the things you care about or a lot of the problems you want to solve in the world are governed by things called differential equations, equations involving derivatives. Derivatives are sort of the fundamentals of calculus. But the problem is, oftentimes, it's really, really hard to solve these things by hand. And the truth is, the majority of equations you're going to encounter out in the real world involving calculus, involving derivatives, you usually can't solve by hand. And so you need a computer. And what a computer often does is they convert these differential equations into linear systems. Because linear systems, we know how to solve because we have linear algebra. If you, let's say you want to be a data scientist, suppose you want to work for a company and do data analytics, or maybe you want to be someone in machine learning. If you're given a data set, it's often really important to be able to understand what variables are important and what variables don't matter so much. And one way to do this is, given a data set, is to try to recognize directions in which the data varies a lot or where it doesn't. So if you look at this picture down here, you'll see in this direction, more or less left to right, the data really varies. But if you go top to bottom, it doesn't really vary so much. And one way to actually compute mathematically the directions in which the data varies a lot versus varies a little is through something called principal component analysis, which is really just another really interesting linear algebra problem. And so these are the sorts of things I work on, trying to come up with linear algebra algorithms that can solve problems like linear systems or eigenvalue problems really, really fast. And so I hope this sounds cool. I hope this has got you excited about math, but I do always feel the need that if what I've described to you isn't fully your jam and this isn't fully something you're interested in, I want to stress that paying attention in math class, just enjoying math is important for life. And I want to talk a little bit about why does math matter sort of more broadly. And to help me, I've roped in some XKCD comics. So first of all, why does math matter? Because math is really the foundation of so many different disciplines, from physics to chemistry to biology and even social sciences. If you want to try to predict something or forecast something, which many people want to do in a wide number of fields, from business to politics to whatever it may be, and it turns out one of the best ways to predict something is to use numbers. And also, math helps you just in your daily life so that you're less likely to be misled and you're sort of more capable and able to understand the things that you see and encounter in the world, to help you understand and deal with things like correlation versus causation, or understanding sample bias, and just understanding how to read a graph, let's say. These are things that are going to help you in your daily life. And I think that math, regardless of whether or not you're going to become a mathematician or a scientist who needs to use math every day, I think math is going to have a really important part in your life. So that's my talk. That's my advertisement for math. I hope you all are excited about math. I hope you're all ready to become budding mathematicians or scientists or whatever it may be. And I'm really excited to hear what questions you all have for me.
Fantastic. Thank you so much, John. I think you're totally right. Based on the Q&A, we do indeed have a lot of future mathematicians with us. And I wanted to start out with a question from a Nord Anglia student named Maria. And Maria wants to know, did you have any mathematicians that inspired you?
So I did. So this math class I was talking about, when I got to take what was functionally a calculus class in college, this professor, a guy by the name of Vadim Koloshin, this guy had a huge impact on me. First of all, this is the first time I had ever really met and interacted with a mathematician. Going through high school, middle school, I always did well in math, and I always liked math. I always liked using math to solve problems, but I didn't even know what a mathematician was. As far as I was concerned, if you only focused on math, the only thing you could do was be a math teacher and teach like high school math. And in fact, even my first year in college, this sort of shows you you think college students know a lot. No, we don't know a lot. I'm taking math classes in college, and there's people teaching me math. And I think, oh, these people their job is just to teach people math in college. They don't do anything else. And so this whole time, the perception is all you can do with math is teach. And then I came to realize, no, you can actually do mathematical research. You can use math to solve interesting unsolved problems. And not just in academia. The NSA is actually one of the sort of greatest employers of mathematicians because mathematicians know how to solve problems. Hedge funds hire mathematicians in droves because mathematicians know how to solve problems. Google, Facebook, Amazon, Vegas, all these places hire mathematicians, not because this mathematician is trained in specifically what they need them to do, but because mathematicians know how to solve problems. And so little did I know, mathematicians actually sort of solve a wide range of problems in sort of a wide number of fields. And so it's actually a pretty good thing to major in as an undergrad. And this professor had a profound impact on me because this is someone who took me under his wing and introduced me to higher level math and really showed me the things I was capable of.
That's absolutely amazing. And I think a lot of us are going to have similar experiences as we continue our educations as well. So I think a few of the students mentioned early in your presentation that they also did those kinds of puzzles you showed us. And we have a couple of students who are wondering, do you still do puzzles today? And if so, do you have any particular kinds of puzzles you enjoy?
Yeah, of course. So I should mention that I have a 3-year-old daughter, and so I do some puzzles with her often. So she really loves. I don't know if you all have ever heard of Rush Hour. So it's a little game where you have, like, let's say a square grid, and you put cars in like a parking lot almost, and you need to maneuver the cars forwards and backwards in different directions so that you can get your car out of the parking lot. And so my daughter has one of those, and she loves playing with this. So we'll take a card, we'll set up the sort of like the traffic jam, and we'll have to move cars to get our specific car out. And she loves doing that. For me personally, I like solving a lot of like chess puzzles. So that's one aspect that has been really enjoyable for me. There are certain sort of chess positions called chess studies, which are puzzles, which are not like normal chess positions, but puzzles specifically made to sort of be interesting or unexpected in some way. And it makes use of chess pieces. Like for instance, here's like a chess study book I just have on my desk. This is like the book I'm going through right now. So
that's amazing. So that really goes to show that, well, two things I drew from that is we're actually interacting and thinking about math at all ages. It's everywhere in our lives, basically, right? And then second, that, that there's so many applications to math we could do in the future. And there's a lot of games involved in that. And a lot of these students may play chess or they may play these strategy games, and there's a lot of math tied up in that. So that's totally awesome. Now we have a student who's wondering, I think they might be a student athlete, and they're wondering, how did you balance your athletics with doing math at the same time? Did any of those two take away from the other at any point?
no, that's a great question. The first thing I need to say is that I do think when you're doing multiple things and you're doing multiple things at a high level, these things take up a lot of time. And so it's important to understand that if you're going to do multiple things, like pursue some degree while being a serious athlete, you have to understand that we don't have unlimited hours in the day and that some things take away time from others. And the best advice I can give you is to make sure that if those two things are a priority, that you start to let other things sort of go by the wayside. Like maybe video games, maybe you need to sort of like decrease video game time or TV time and really focus on the things that are most important. And so for me, when I was playing American football while sort of getting my degree, like let's say as an undergrad in college, the important thing was I focused on those two things first. And those two things were the most important things in my day. And not just that I did them first, but I made sure that I enjoyed doing them and that those were the things that I really wanted to do first. Because I find that when you're really busy and you're really tired and you're working a lot doing these two things and they take up a lot of time, it's really hard to do unless you really, really love what you're doing fundamentally. And so that's another piece of advice I'd say.
Yeah, that makes a lot of sense. So prioritize the things you love and that you want to spend time on and get better at. That makes total sense. So we have a lot of students who are taking math right now, listening in on this call. I'll let you into a little secret. I'm in a biostatistics. I'm in a math class right now as well. And I think we're all wondering, how do you deal with facing difficulties in math? So what if you come across a really hard problem? You gave us that wonderful example of the problem in the chaos book. But nowadays, how do you overcome something that seems a little difficult or insurmountable at the time?
So first of all, I should say, sometimes you don't. And this is one thing that's interesting, and this is one thing that's fulfilling about trying to solve difficult, interesting math problems, especially problems that people haven't solved before. There's something interesting about the uncertainty of not knowing if you're going to be able to solve this problem. And sometimes I'm working on a specific math problem, I'm working on something, and I just can't solve it. And I'm trying and I'm trying and I'm trying different things, and it really just doesn't work. And that's okay sometimes. That's part of the process. That's part of getting better. If you just solved every math problem you came across like that, then something tells me either you're like the smartest mathematician in the world, like you're the next Terry Tao, or you're not really challenging yourself. And I think it's important to understand that struggle is part of the process. Struggle is actually how you get better. If you're going through life or you're going through school and you feel like you're never struggling in math class, or you're never coming up against something where, am I going to be able to solve this? Won't I be able to solve this? I don't know. Is this challenging to you? If you don't sort of feel these things, then I feel like you should probably try some more difficult things, at least outside of your classroom, because the way you really improve, the way you really get better is by challenging yourself and trying to sort of stretch yourself. And that's the biggest piece of advice I can really give, is that, yes, sometimes I come across problems that I don't know if I'll be able to solve. Sometimes I come across things that are really, really challenging. And I revel in that challenge. And I enjoy that challenge because through that challenge, that's actually how you make your biggest gains, your biggest sort of like improvements as a mathematician or as a scientist. And so I really approach them with a positive mindset about I'm coming across something that's really challenging me. I'm going to understand that me getting this problem right or wrong says nothing about my self-worth or my ability to do math, but that this is an opportunity for me to like try to grow as a mathematician.
That makes a lot of sense. And I think we could apply that to a lot of sciences or any research field as well. So that's totally wonderful because I think we have a lot of future researchers in our midst today. We have a student who's asking a really interesting question about football and mathematics, and they're wondering, did your skills in football ever help you solve math problems or vice versa?
I think the football skills it has helped me in math a little bit. I feel like, first of all, football teaches you American football teaches you a type of toughness. You're often getting knocked down. And especially if you're off your game a little bit, you get really punished for it. And in football, you really need this sense of resiliency that no matter how many times I get knocked down, I'm getting back up. And this sense of accountability. And I think this sort of approach is something that's really helped me in math to sort of keep going and keep pressing on where someone else might have quit. And so that's something that I think football really helped me with. The other thing that football helps with, and this isn't just a football thing, but I would say this is something that I think every young person should experience, is being a part of a team. So being on the football team, my teammates depend on me, not just to win, but also for their safety and their well-being, and I depend on them. And one thing that I noticed when I was in middle school or high school, I felt like I never really understood the dynamics of teamwork, the dynamics of working with a bunch of people towards a common goal. And it turns out that in the real world, like when you grow up and you get a job, almost any job you do, you're going to be part of a team, and your success is going to be intimately intertwined with the success of others. And so one thing that football really helped me with is just teaching me how to be a functioning member of a team, working towards something greater than myself. And I think for every young person, I think it's important to be a part of a team at some point in your life. It doesn't have to be football. It can be volleyball or soccer, or it could be the drama club. It could be the debate team. It could be the chess club. But being a part of a group or a team at some point, I think is a really good lesson. And that'll help you not just in whatever you're doing, but it'll help you professionally.
And speaking of lessons, John, we have a few students who are in fourth or fifth grade right now, and they're excited by the prospect of doing math and they want to do more. They're wondering, can you recommend some resources or math books or problems that they can do for fun as well?
Yeah, absolutely. So one thing that I loved to do when I was a kid, which I think is pretty fun, you can, let's say you're in math class, whatever math class you're in. I think a really fun thing to do is like, just read ahead a little bit. So first, my first piece of advice, because, okay, somehow I'm impatient, like imagine you're in fourth and fifth grade and you're reading the, recent Harry Potter book, and you're reading it with class and they're saying, okay, we're going to read a chapter a week. And you go through the chapter every week, but that book is gripping. Are you really going to be able to wait to read every chapter like every week? You're going to only read a chapter a week? No, like if that thing grips me, I'm reading that thing. And I'm sorry, I can't do one chapter a week. And so I would say that if you're really enjoying math class and you have a math book associated with your class, there's no reason you need to wait for the teacher to sort of like get to a certain place. When I was a kid, it was like reading a Harry Potter book. Like I want to read to the end. I want to know what happens. I want to know what's going on. And so I would just read it myself. And I would say, once you do that, my advice to you would be get the book for next year. And just pretend it's like it was like the next Harry Potter book for me, and go through it and try to learn and try to sort of like just enjoy it. So that's what I would say with respect to formal math. And then with respect to informal math, I think getting puzzle books are a great way to sort of train your sort of like creativity, your quantitative reasoning, and I think it'll just make you a better scientist. So I would recommend, maybe a Martin Gardner puzzle book. One puzzle book I really like and that I often recommend to young people is this Moscow puzzle book. If you just Amazon like Moscow puzzles, 365 puzzles, I think. This is a really good puzzle book as well. And so there's a lot of different cool options you can get.
Got it. And yeah, from personal experience, if you ask the math teachers for next year's book the summer before, they will give it to you. So I've been there for sure. We now have a couple of students are wondering, did you ever participate in any math competitions? I think maybe they're thinking of the ones that people in math club do, but did you ever do anything like that, John?
So I did some in middle school. So I actually did take part in math counts, and that was a really enjoyable thing for me. It was just really fun solving like cool, interesting math problems. In high school, I didn't do any math competitions. I have to say, in high school, I was very much sort of like a typical sort of like high school student. Like I was, I would read math and I would read interesting things, but I was spending so much time like playing sports and, being a football player and just doing silly things with friends that I never took part in like math Olympiad or anything. But yeah. And the one thing I would say is that if you enjoy those sorts of things, that's great. If you find that you don't do so well on those, that's also fine. I feel like there's often a perception that if you're not great at, let's say, math Olympiad, then you can't be a mathematician. And that really couldn't be any further than the truth. Because, for instance, even at MIT, like we're made up of lots of professors who did not do very well on the math Olympiad. And the fact of the matter is, as you progress further and further along in math, it's not about how quickly you can solve a problem. It's not about being able to solve, 4 or 5 problems in 2 hours. It's about being able to solve one really tough problem or 2 really tough problems in a year or in months, and you really dig in. And so I would say this ability to do math really quickly on the spot becomes less important the further along you get. And so if you're not great at doing math really quickly, don't let that discourage you at all, I would say.
That's definitely really good to know and very reassuring for sure. So we have a few students who learn the basics of coding while they're in grade school. And a student has noticed that there's a lot of letters and symbols and numbers in math. And they're wondering if you consider, John, math a language, like in coding.
Yeah, no, I do think math is a language. I sort of think of math kind of like our universal language, like a universal language for the world to sort of cope with and describe like the physical world we live in and the sort of quantitative things that we deal with. And I think when you think about the earliest uses of math, it really comes out of that. And the majority of things you learn in math actually grow out of some real world issue or problem that people face in many, many instances.
And kind of following that line of thought, and you're working with these real world problems that can sometimes be pretty complex. A student's wondering, what kind of tools do you use to do math? I mean, is this all pencil and paper? Are you using calculators? Are you using computers? Can you tell us a little bit about that?
Yeah, absolutely. That's a great question. So I'm generally thought of as what's called an applied mathematician, because I usually work on sort of problems that we face in the world. And also some people may think of me as a computer scientist. But the interesting thing is that although the majority of my research involves coming up with interesting tools and techniques to solve problems using computers, I actually use a computer very rarely. And the reason is, once you know how a computer works, you know that a computer will only do what you tell it to do. And so when I'm trying to come up with a way to solve a problem, I know what the computer can do for me. And so I can do a lot of things using pencil and paper, knowing that what I write on my piece of paper, I can tell a computer to do exactly. And so a lot of it is me thinking through how to solve the problem. And only then will I go to the computer and then actually code and tell the computer to do what I want it to do. And so the majority of my time is actually spent thinking, using a piece of paper and a pencil, trying to think about how to solve the problem. The aspect of taking my paper solution and then telling a computer to do the associated thing, that actually takes not too much time, but that's also an important part, because sometimes you think up a way to solve a problem, and then when you tell the computer to do it, you realize or recognize flaws in your idea that you didn't see before. And so both parts are important.
Got it. And now we have a student who's wondering, how can they build their confidence in their abilities in math? What if they think that they're bad at math? How can we correct that and help and show people that math is all around us? What do you say to that?
Yeah, absolutely. That's a really common and good question. If someone says, I'm bad at math, I usually find it's a combination of one of two things. First of all, math is one of the rare subjects. Math, it's not really like history. It's not really like biology. What you learn in a given math class, you need that for next week's lesson. Often what you learn in a given year, what you learn in fourth grade, you're going to need that for fifth grade. Learning math is like building a house. It's really, really important that you have a solid foundation at every level. Otherwise, how can you expect to like build a roof on a house when the base of the house is falling apart? It's just not possible. It's really hard to do. And in a similar way, I think that when people sometimes say they're bad at math, it often means they're in a math class or they're in a situation where the things they're learning in math rely on things that they should have learned before that maybe they didn't fully understand or fully learn because they got a good enough grade to get by, but no one ever stopped them and said, hey, I don't think you really understand this, and this is going to be really important going forward. So that's often one tough thing. I think one way to try to fix that is it's good to take a step back and ask yourself, what are the things that I struggle with math that people think I should already know? And there's nothing wrong with just going back through that material to make sure that your foundation is solid. Because if you don't have a solid math foundation, you're just already setting yourself up to fail. And that doesn't feel good. That, I say, is the first thing. And then the second thing is, often when people think about math, I feel like there's this focus on, I have this problem I have to solve. It's about getting the right answer. And if you get the wrong answer, it's a failure. If you get the right answer, good, check mark, move on. And I think the better way to think about math is trying to solve problems like you're solving a puzzle. And if you can't solve the puzzle or you get the puzzle wrong, that's okay. But the important thing is to focus on your thought process, to focus on, how did you come to this answer? What step in your thinking was maybe a little bit off? And try to learn from that. Or even if you got the question right, taking a step back and saying, what about my thinking process was good? What did I do well? And try to internalize that and think about math as less of a constant checking or challenge to your like intelligence or your ability, but rather just opportunities to try to hone and improve your problem solving skills. So like you're just sharpening a knife every time you're solving a problem, because you want to be sort of as sharp and as like good as possible, so that when you encounter some problem that you need to use math to solve, you're prepared. And I think moving away from the focus on getting the right answer, getting the wrong answer, or moving away from the ability to get math questions right being sort of like intimately tied with intelligence or something, I think really is I think these are things that can really sort of help people who say they're bad at math.
Got it. That makes a lot of sense. And I think following up to that question, John, we have a student who asks, how do you remember all of these math rules and concepts after years and years? So you're not looking back, 1 year, what you learned last year, you're looking back many years. How do you remember all of it?
I don't. No, I don't. So first of all, if you think, so let's suppose, so often, you learn different things in different areas of math. I have news for you. I don't remember all my trig identities. I don't. And the important thing to remember is I don't need to. It's not so much about making sure that I memorize every single math formula there is out there. That only helps you to a point. What I remember and what I internalize, and it's not like memorizing anything, or it's not like, some like formula in my head, it's understanding and internalizing ideas, techniques to solve problems, tools you've seen before. It's the same. So the way I would think about it is it would be kind of like asking someone, how do you remember how to ride a bike? Or how do you remember how to do the dishes? Or how do you remember how to make your bed? This isn't some formula that I have locked somewhere in my head. It's something that I know how to do because I learned it at some point and I really internalized it. And so I would say that the majority of math things in my head are not formulas that I'm just going to spit back out at you. Yes, I've learned a lot of formulas through math because I use them a lot and they become internalized. And some formulas are useful to know, like, the area of a triangle or certain tools and techniques in calculus or algebra. But those are really just the basic building blocks. The important thing that I remember is the tools and techniques, remembering how I solve certain problems. And that's what really helps me, because when I'm sort of solving a problem, suppose you're an engineer or you're a scientist or a mathematician like me, if I come across a problem and I say, oh, I think there's this formula I used to know that I think could be useful here, but I don't remember the exact identity, Google it. It's on Wikipedia. But what Wikipedia can't do for you is it can't tell you, oh, you have a problem of a certain type. I remember a sort of idea I can use to try to solve this problem. That's the sort of thing that is really important and is really valuable. So.
Fantastic. Now, John, we have so many questions, unfortunately not as much time to answer all of them, but I wanted to ask one concluding question before I quickly talk about next month's abstract for the students. So I think that you have inspired a lot of folks to consider becoming mathematicians or to use math more every day in their lives. And what qualities do you think good mathematicians have? What qualities can these students cultivate today?
I think the single best quality for a mathematician is creativity. I think it's really important when you're faced with some mathematical problem or a problem in whatever discipline to really take a step back and really try to think about the different ways you could try to solve it. And I think being able to be creative and think independently and think for yourself is a really important tool and technique, because just learning and remembering ideas that other people came up with and just using those sort of like black box will only get you so far. And so I think that's a really important thing for a mathematician to have. I think curiosity is really important, just an innate desire to understand things and see how things work. And then also just a sort of sense of discipline and rigor to make sure that you really understand everything inside and out, and that you aren't sort of like leaving any gaps or any holes anywhere. So.
That's absolutely excellent advice. And now, John, I'm going to spend a moment introducing next month's abstract. So John is an applied mathematician and applies math to all these really complex real world problems. That's quite similar to what our next speaker is going to do in a month from now. We're going to have Margaret Duffy, who studies climate science, and she's going to be giving a talk called Climate Science for the Future, and she uses math in her climate models. So if you love John's talk and are as inspired as I am today, then we can continue to ask math questions next month as well. And with that, I'd like to thank John sincerely for his time today and for sharing with us all this thoughtful information about his work and his advice to all of us for doing mathematics. So thank you so much, John. We really appreciate having you here.
Absolutely. Thanks for having me. This has been a lot of fun.
It really has. And I'd also like to give a quick shout out to Nord Anglia and the Nord Anglia community. Thank you so much for supporting us and for making MIT Abstracts possible through the MIT-Nord Anglia collaboration. So thanks again, everyone. I hope you enjoyed it, and let's go do some math. Fantastic. All right, goodbye.